Today I'm going to go sort of one level down into what's called the network layer. So as you know from the last few lectures, at the top level of the internet we have what's called the application layer. This is sort of where all the applications live. And then we have the API below that, which is how we establish these pipes between the different parts of the application, and that's sockets, which we talked about a couple of weeks back. And then what you learned in the last 4 lectures is how do we get reliability and flow control over end-to-end paths. So if you think about it this way, if I go back to the earlier picture I had, we had sort of the application over here, and that's other end of the application. It could be a client-server application, for example. And then we had the socket, which connected it into the, that was the API, the programming interface into the cloud. And then we had this sort of internet cloud. And what you found out actually is there's a transport layer over here underneath, which provides reliability essentially and flow control. But then we still have this notion of a pipe underneath the transport layer. The transport layer doesn't really do much other than add reliability over this pipe. So what we're going to talk about in the network layer is how we build this pipe. Okay, so we're going to ignore everything above it and just focus on this part over here and say, how do we build a pipe? Okay, in other words, if I have some end system, we will call that a host when you talk about the network layer. There's some host here and some other host over here. How do we build an end-to-end path between the two? Okay, and that's the focus of the network layer. And so, as such, we have to have 3 concepts that are important. One is called addresses. Oops. The second one is called forwarding. And the third thing is called routing. So addresses is what you'd expect. You know, if you want to send somebody a letter, on the letter I put their name and then I put the address, and then the postal service somehow figures out how to deliver it to them, right? And so what we put below the name on a letter is the address. Okay, address is a unique way, hopefully a unique way of identifying some destination or endpoint or host. Okay, and actually, as we know, we have to uniquely identify an endpoint, we both have an address and we have a port number, but we're going to ignore the port number. Right now, we just want to get to a host, and then the transport layer will demultiplex based on the port number. We know how to do that, so there's no need to worry about that. So that's what an address is. What is forwarding? Forwarding means that in between this path is actually not a single pipe. We actually have these elements called routers, and the routers need to forward the data. They have a packet that comes in with some header, and that packet is given to the first router, which gives the second router, the third router, fourth router, all the way, and they kind of hand it off. Just like in the mail service, you put your letter into a mailbox, and then the postal carrier picks it up and takes it to the post office, and then they take it to the next post office, and so on. So each intermediate point is forwarding the letter. In the same way, we're forwarding the packet, so that's forwarding. Okay? And then routing. What is routing? Routing means figuring out how to forward it, where to send it to, right? So if you get a letter that's addressed to some other place, some other country, let's say you're sending it to Ireland, so you'll put the address in Ireland, you're going to put the address in Ireland over there, and then the post office is going to, postal carrier is going to look at it and say, oh, it's not Canada, it has to go somewhere, and they're going to send it on. Eventually it's going to get to Ireland, right? So what is the algorithm? What's the process by which the postal service determines where to send it to next? You know, if it says London, should I send it to London, Ontario, or London, England, right? That's a decision that needs to be made, and that decision is made using routing. So that's the 3 things that the network layer provides. So the network layer is called the network layer because it actually provides the network. I mean, without it, there is no network. Okay? So another way of thinking about network layer is to think like this. Okay? So let's see if you guys can identify what this is. So I'm going to draw this in 3D perspective. So let's see. My 3D skills are not so great, but we'll try anyway. Let's see. Okay, who can identify what that is? It's not badly drawn, actually. Yeah. Beg your pardon? A puzzle piece. Not really. Let's imagine there's many more of these. Yeah.
Is it kind of like a train track?
A train track, thank you. It's a toy train track, right? If you've seen those Christmas trains, you have these little segments of track, and you kind of snap them one to the other, right? And then you get a train. You get a track that you can run on. The network layer is this stuff over here, the goo that keeps the tracks together, okay? Without the network layer, all you have is a bunch of links. Each track segment can be viewed as a link, right? And a packet is like a train, okay? So you want to send your packet, this train, from one end all the way to the other, okay? To do that, you have to make sure you can hook up these things together. And moreover, when you have a piece that looks like this, a switch, right? You need to know whether to go this way or that way, right? And in a train track, you have a little lever thingy, and you pull and push it, and makes it go one way or the other, right? And that's exactly what you need to do. So addresses tell us where we want to go. Forwarding is a process by which we snap these two things together, right? So they form a path. And routing is making those decisions where the train is going to go. Okay, so if you know how to draw a toy train or a train network should work, it's the same thing for computer networks, and the same thing actually for road networks as well. You come to a decision point, which is a traffic intersection. Do you go left or right, or go straight, right? That's a routing problem, okay? So all of these issues of addresses, forwarding, and routing exist in all networks. They exist in computer networks. They exist in train track, toy train networks, real train networks, and actually even in biological networks, right? So if you take a drug, right, that's supposed to cure your headache, the molecules that go into your body are supposed to go to wherever you're having pain, wherever it is, right? It has to go there. So how does it go there? What we do is we do broadcast. We put it in the bloodstream, and it goes everywhere, right? That's broadcast. Give it to everybody, and maybe they'll pick it up. But a smart drug is supposed to find the right route to the right destination, just go there. And how do we do that? Well, that's a different topic, but people are actually investigating exactly these, what are called biological networks or nano networks, which have these properties. But we won't talk about that over here. Okay, so having set the stage for what the network layer is supposed to do, let me kind of just remind you about one thing, which is that this path over here is hidden to the transport layer. From the transport layer's perspective, it sends a packet, it just gets there. What is exposed are the attributes like delay, like throughput, reliability, security, to some extent cost. All of these are exposed, everything else is hidden. From the perspective of the transport layer, you give it a packet and magically gets to the other side. Okay. Any questions about this so far? Yeah?
Is network layer only how it does those things, or the hardware associated with all of them?
Both. So I'll come to how the hardware looks like in a moment, but we refer to the underlying hardware as well. The hardware carries out network layer and physical layer and link layer activities, right? So all hardware does many layers. Like your end system, your computer, is going to do the application layer and the transport and network and link and so on. So we can't point to this and say that's the network layer. No, that network layer carries out activities that belong to the network layer. All right, so now I'm going to show you what I call the cartoon guide to internet. So I kind of woke up early this morning and I was wondering how to explain to you how addresses work. And then it occurred to me that I could actually do it by means of a series of cartoons. And this is going to be, I believe, really easy to understand. I just need my magic color markers. Okay, good. So let me start by first telling you what an address is. An address is a string of bits, okay, zeros and ones. And in the most commonly used address on the internet today, as you know, is the IPv4 address, 32 bits, right? So for now, I'm going to make life simple. I'm going to make it easy. I'm going to assume it's just 4 bits, okay? I'm going to look at 4-bit addresses. I'm going to draw them like this. I'm just going to talk about, so I have 16 computers. And each computer has a unique address, and they have 4 bits. So obviously, the numbers are going to be 0000 to 1111, right? So let me just write that out. So Oops. Okay, so I have all 16 computers like so. And now I want to, I've figured out the addressing problem, which is I give each computer its own address. I just say, here, it's your address, take it, you're done, right? So 16 computers, 16 addresses, addressing is done. Now let's think about forwarding and routing. How do we do it? So the first solution I'm going to propose to you is the following. And for that, let me use the green solution. And the green solution looks like this. I put a single hub or single box, I'll call it R for router, and I'm going to hook them all up like so. Okay? So what does the solution mean? It means that I have a single box which has 16 endpoints. Endpoints, I call each of these a port. Okay? That's what's called a port. 16 ports. So like, if you have a hub at home, you've seen those little slots where you stick in your Ethernet cable. Right? Everybody's seen those little things, right? So those are called ports. I have 16 ports, 16 addresses, 16 wires and 16 ports, and I'm done, right? Because what does forwarding mean? Well, I get in a packet from 1101, let's say to 0110. It puts in the destination address. It says, I want to go to 0110. I say, oh yeah, that's port number this. I put it over here. It gets there, and I'm done. Okay? No problem. What's the routing problem? The routing problem is trivial. Whenever somebody comes in, you say, oh yeah, port number 4 is this, port number 6 is that, port number 7 is that. I have a little table. And when I look at the destination address, I see it goes to port number so-and-so. I stick it in there, and off it goes, and it's done, right? So why don't we build the internet like this? Why not have one single big router in the sky? Okay, everybody connects to it. Any suggestions why not? Yeah? It can be taken down. Well, that's not really true. I mean, we'll put military guards around it, and so on. Yes?
Slow.
Why would it be slow?
Because it's taking in requests from everyone and routing all the requests.
Right, and how many is everyone?
A lot of people.
A lot of people is not mathematical, Give me some number. How many endpoints do you think there are?
I don't know. Millions, obviously.
Millions? Really?
Over 2 billion.
Over 2 billion? Yes?
Is it like an infinite amount?
Beg your pardon?
Infinite amount, because you just keep adding more and more to the network.
Oh, we can't add more and more because remember we have 32 bits. We have only 2 to 32, and then we can get a bit more, but not that many. So the numbers today is about 7 billion endpoints on the internet, and we're expecting to go to about 15 billion in the next few years. Okay, 15 billion because all sorts of random things like clocks and toasters and cell phones and whatnot, which is called the Internet of Things, is going to come. So you have 15 billion ports. It's kind of a large router. Where are you going to put it? The only logical place is the center of the earth, and it's too hot over there. So it's not scalable. So that's what we say. It's not scalable, and it doesn't work, right? So actually, there is the 0th order solution, which I forgot to mention because really even more stupid. So I'm going to draw it just because I want to. The 0th order solution is to have wires going from one to every one, right? Like so. This is the tin can and string solution, and I'm going to have basically 16 squared wires, more or less, right? And I can do this with the yellow to each one of them like that, right? I can do that always. And everybody has a direct link to everybody else. That's too many wires, okay? I need 15 or 7 billion squared, right? Which is like 49 million trillion or something like that. It's too many numbers, too many things. 49 to 10 to the power 24. It's too many wires. Okay? We don't have enough copper in the world for that. So that doesn't work. The first order solution is to put this one router in the sky. That doesn't work either. Okay? So all right, we'll try something else. What we'll do is we'll keep the addresses the same. And I'm going to now erase the yellow and the green solution because both of them don't work. And I'm going to try something a bit more clever, but not clever enough, as it turns out. So what I'm going to do, just a bit more clever, is I'm going to have not one router, but 4 routers. Okay, so let me now draw these 4 routers in green, and I'll draw it like this. These are my 4 routers. What I do is, I'm going to make a network between these four like this, okay? It's a fully connected network, okay, between these four routers. So any router can get to any other router in one hop, okay? It's just from drawing it. That's not a problem. Now what I do is somebody comes to me and says, I want to get IP address, so I want to get address 1011. I'll just give it to a randomly allocated router. So that one goes there, this one goes here, maybe that goes there, that goes there, and that goes here. And I just make sure that nobody has more than 4, but as long as that constraint is available, it's 1, 2, 3, 4, I don't mind sticking anybody wherever they want. So it's 1, 2, 3, 4, for example. So this is one allocation of addresses to routers, okay? Random. Okay. Now, this solution actually is scalable because you want more addresses. What you do is you put another router over here, another 4 like this, like these guys, make them hook up like so, and then hook one of these guys over here, and then this whole cloud you kind of replicate like this, like that, right? And then you can make it go, and you add one more bit, or sorry, 2 more bits, right? Okay, so I think I lost you. So let me go once more over this again. Let's go with this solution first, okay? So what does the solution mean? I have, instead of one router, I have 4 routers. So each of them has 1/4 the load, right? As opposed to having one big router in the sky. So let's say 1011 wants to go talk to 1100. So 1011 goes to its router. The router says, oh, I have 1100, and it just sends it like this, just like the first solution, right? But let's say 1011 wants to talk to 0011. So 1011 goes here, and this one says, 0011 isn't one of mine, all right? But somehow, magically, I know that 0011 belongs to this router, so I'm going to send it to that router, and then that guy sends it out over here. Okay? Is that clear? Similarly, if I wanted 1011 to talk to, let's say, 0100, this guy has to magically know that it's available over there. It sends it down here, and then it goes off over there. So we have this magic step, the routing step, which tells us which of these other routers is responsible for one of these addresses. Okay? What is this magic? This magic is just a table. Okay? It's called a routing table. And the routing table looks something like this. It has basically the destination and the next hop. And the next hop, again, to keep this clear, I mean, it's a different color now. I'm going to give these numbers, let's say 00, 01, 10, 11. So for example, at this router, if I have 1100 and so if the destination is 0011, then the next hop is 01. So destination is 0011, next hop is 01, and so on. We can fill in the table, right? For example, at this router again, so this is for table for 00. So if I say destination is 0111, then the next hop is 10, 0111, next hop is 10, okay? And so on. Does everybody see how to fill in the table? So for every destination that is not a local one, we need to have the next hop router. We send it to that router, and that router says, oh yeah, that's mine, and off it goes, okay? Any questions about this? Everybody get it? Okay. The problem with this is that these tables over here are not that scalable. Because if I have, let's say, 7 billion endpoints, right? The endpoint itself doesn't have to do any work. The endpoint just takes a packet and gives it to the router and says, here, you deal with it. I don't know. This router needs to know the next hop for every single of the 7 billion endpoints. Why? Because there's no logic here, right? 0011 could be here or here or here. You don't have any idea. Could be anywhere. So you need to have a table that says the next hop for each different destination. So these tables become very, very large. Okay? Any question? Yeah?
So you mean like every router hosts one of these tables?
Yes, there's a table for each one of them. It says for this destination, what's the next hop? Okay? And the reason why it's very large is because this is a random allocation. I have no idea where to go next, right? Yeah.
Okay, maybe I didn't really understand the routing table.
Okay, sure. Yeah, let me go over it again, and then we'll take a break because I think you guys are throwing too much stuff at you. So I have a packet from, let's say, 1100, and I want to send it to 0011, which is over here. So that's the source, and that's the destination. Okay? What this does is to put the packet and give it to its router, which is 0000. Sorry, 00, this one over here. This router has to figure out whether to send it here, or here, or here. How does it do that? It looks at the routing table. Okay, the table says, magically at this point, we're filling this table somehow. It says, 0011, you should be sending it to 01. So it sends it to 01. 01 says, yeah, that's a local port. I know what to do, and delivers it over here.
It's just magical.
For now, it's magic, but in 2 lectures, we'll explain what the magic is. Right now, the routing table is created by looking at the whole thing, for example. Yeah. Yes?
Couldn't when you pass up to your central router,
Yeah.
That broadcast to the rest of them?
Yeah, it could. It could broadcast to all of them, but that would be wasteful, right? So you could say, I don't know the routing table, I'm just going to give it to everybody. But imagine you have 7 billion endpoints, and every packet is given to every router. That's even worse, right? That's not going to work. Any other questions about this? Does everybody understand what this routing table is? Note that the routing table is going to be different. For example, at 10, what is it going to say? Table at 10, it says, for example, 0000 is going to be at 01. So the destination it's going 0000 is at 01, and then the destination, for example, 1101 is at 00, and there's some more entries. There's going to be actually 12 entries over here. It's going to be 12 entries here as well, okay? Because this is everything that's not your own. Everybody understand what's going on here? So there's routing, there's forwarding, and there's addressing, all kind of tied together. And you can see that this one has a problem, which is large tables. And in the next step, we'll make it simpler. We'll see how we can make it much easier, but we're going to give up something for that. Okay. Any questions? Okay. Yeah.
I think for table 10, regards of that,
Yeah.
you probably should have, if the address is not in the list,
Yeah.
then go to 10, 10. So for other people.
Oh, if it's a local thing, we assume you know it already. You could say, I guess there should be one link here which is missing, but this goes, I don't know where. Maybe it goes there. It should say that I'm responsible for these 4 addresses. Yeah, we sort of have plus local ports. Right? We have the local ports like before, which is this address belongs to my port number, so you know that it's local. Yeah. Okay, I forgot to post the problem set. I'm going to actually post it right here. The thing is, the problem set is going to make no sense at all, but anyway, until the end of this lecture. So, what are 2 consequences of all? Okay. And you're saying, what does that mean? Those are the 2 questions for this, and I'll put them on Piazza as well. Okay. All right. So we'll get to both, and actually, we'll get to both of them in a few minutes. Okay. So I want you to just raise your hand if you understood this. Okay. All right. Good. Or maybe I should invert that. Who did not understand this? Okay. Excellent. Okay, so it was easy. Okay, I thought it was easy because I was trying to explain it to my daughter and she got it, and she's in grade 8. Okay. The problem with this approach is that every router has a very large table. So you know what? We can fix that, right? How can we fix that? Should be pretty obvious from this. How do you think we can fix this issue of making the routing tables too large? Yes, Brian.
You can is instead of having them linked to each other,
Yeah.
maybe like just random links.
Yeah.
As long as they are all connected.
Yeah.
And then, for example, for the first one, you say, oh, I only hold this to these 4 links.
Yeah.
And then can tell like have a table say, for example, it's connected to 0, 1. Let's say, as long as it's not those 4, ask 0, 1. And then 0, 1 holds 4, right?
Yeah.
And 0, 1 say, as long as it's not these 4, then ask the next one.
Okay, so your approach would be to take the packet and essentially, instead of broadcasting to everybody, give it to each one and ask, do you have it? No. Then you go to the next one, do you have it? No, and so on, right? That makes sense if you're able to, and this is how, by the way, Nutella works. This is how peer-to-peer networks work, right? Where you ask somebody, do you have this? No, okay, broadcast, you send it out again. But you can have fairly long paths because, these 4 look close by, but that could be in a Mountain View, that could be Beijing, that could be Moscow, right? So you're going to go to Beijing, do you have it in your 4 billion? Sorry, no, okay, we'll go here, and so on. That doesn't really work, yeah.
We can kind of do it like a telephone, like
Yeah?
there's area codes.
Yes.
So like if you're in this area, then you go to this, like you're linked to this server. So
Right.
you automatically know you have an index of all the areas.
Exactly. So what we do is, what area code is doing is to introduce hierarchy. What does hierarchy mean, right? Hierarchy means that the 0, 0 over here is going to have all the prefixes that start with 0, 0. Okay, so let's redraw this to show you how that works. I'm going to get rid of all the stuff in the middle. Remember, I haven't changed the endpoints in any way, right? I'm keeping it exactly the same as before. All I'm doing is changing the GUI of how the router works. And I'm going to make it look like the telephone network, as Heiji said. So I'm going to call this 0, 0, 0, 1, 1, 0, 1, 1. And what I'm going to do is I'm going to put the yellow wires to the 0, 0, like so, and then the 0, 1, like so, and then 1, 0, like this, and then 1, 1, 1. And then in between them, I'll have the same 4 green lines like I had before. So the routers are just the same as before. They still have 4 ports, right? Each endpoint is connected to one router just as was before. No change there. The only difference is that now we're being systematic in our allocation of addresses to routers. And now what happens in the routing table? Let's see what happens in the routing table. The routing table is like this. Let's say 1100, which is going to be in 11, right? Gets a packet destination for 0011. Okay? Well, it knows that all addresses that start with 00 are with router 00, right? That's the way we did it. So it says, oh yeah, I'm going to go to 00. So this routing table becomes something like this. It says, if the destination is 00 anything, give it to 00. If it's 01 star, star means anything, give it to 01. If it's 10 anything, give it to 10. If it's 11 anything, give it to 11. That's a pretty simple routing table. And in fact, that routing table is going to be the same for all of them. The same routing table for all of them. Yeah?
Actually, what I said is just like this. And,
Okay.
And actually, you couldn't solve the problem that if you need to connect every single router,
Yeah.
then it's still like impossible to do it if the scale is too large, right?
Okay, so
like some routers, they are not interconnected.
okay, we'll come to that. We'll come to that in a minute. Just let's assume that we are able to connect them completely, and then I'll show you how to work with it when it's this part over here. I'll show about that in a minute. But let's go back to the solution just a moment. We're doing something a bit interesting over here. What we're doing is that we are introducing what we call geographical locality. All right. So what we're saying is that all the addresses, because we don't want very long wires, right? We don't want very long wires. We want to make sure that all the addresses that are in the same geographical region have similar IP addresses or similar endpoint addresses. For example, 0000 and 0001, they're both going to have to connect. They're going to have to connect to router 00. Okay, no choice. Okay, because we're going to force that. Because we're forcing that, and we don't want to have very long wires, it means that all the addresses in the local area are going to have the same prefix, 00. Do you see what's going on? What we're doing is we're geographically localizing addresses. Because alternatively, you're going to have very long wires. You know, if a 00 router is in California, I'm going to have a wire going from Waterloo to California. That doesn't make sense. So the Waterloo router is going to be, let's say, 00. All the endpoints are going to be 00, which means that these addresses have geographical significance. Okay? And that's why Geocode IP works. But in homework assignment 1, you had Geocode IP, you typed in an IP address, and it said, oh yeah, you're from so-and-so area. How did they do that? They did that because IP addresses, like these addresses, have geographical significance. They all are belong to some router somewhere. Okay, make sense? So this is beautiful because now we can view the address as having two parts to it. Okay, we're going to have two parts to it. The first part we'll call the network number, and the second part we'll call it the host number. So because 00 for us has a meaning, 00, which is just bits, suddenly becomes the number associated with this network, like so. And this is this network, like so, the 01 network, the 10 network, and the 11 network. We can talk about these being 4 networks which share an address prefix and are connected to a router which we'll call 10, 0011, and so on and so forth. And now we can view this as basically this cloud right here. We have these 4 clouds. Each of them has a similar address, and they have these 4 things in the middle which are connected up over here. And this whole thing you can actually recurse. You can kind of take the whole thing and add one more bit and make it a next level up. I'm not going to talk about recursing right now because I'll talk about that later. But for now, let's just focus on the fact that by doing this geographical allocation of addresses, we can make the routing table very small. Okay, first win. Second win is we have the ability to sort of view this as a network, okay, and which has a network number. Okay. The third thing is that we can actually do something like we do in the names. If you have a name like uwaterloo.ca, University of Waterloo, which owns uwaterloo.ca, can allocate any name it wants. You can give it CS, ECE or math or whatever. It doesn't need to ask anybody for help. It says, this is my domain. In the same way, the owner of this address space 00 can give extensions. Anything to the right of 00 belongs to it. It can do what it wants with it. It can allocate the address or not. Nobody else needs to know, because once it gets to the 00 router, life is good. In the same way, in assignment 1, you saw how University of Waterloo owns the address space 12997, right? Anything that comes after 12997 is University of Waterloo's business. Nobody else needs to know, all right? That's exactly what's going on. So that 12997 corresponds to this. So this delegation is also for addresses. This makes life much easier because you don't need to go ask some central authority, can I allocate this address or not? No problem, just allocate it. It's yours, right? So we get part of the address space. So this kind of hierarchy is a big win, and it is what's done on the internet today. That's why we have a network number, and then we have the host number in the behind. And that's why in assignment 1, if you remember, I said numbers, IP addresses are of the form network number, host number, right? And the first few bits are going to be a network number, as I'm showing over here. Okay, so it's a very powerful idea, and it's kind of at the heart of what happens on the internet today, or actually in any network which you want to scale, and this scales quite well. Okay, so any questions about this? Okay, so to summarize, we started out by saying that we had a bunch of addresses. We had 16 addresses, and they're corresponding to hosts, like I showed over here. And our problem was, how do we hook them up in a way such that we can scale? The first solution was connecting wires to everybody else. That didn't work. Second solution was one big router in the sky. That didn't work. The third thing was to have multiple routers, but to have random allocation. That didn't work because the routing tables were too large. And the fourth solution is to have the routing tables be geographically, the routers have geographical significance, addresses have geographical significance, and that naturally introduces the notion that we have network numbers which correspond to the high order bits of the addresses. Okay? It comes from the fact that we are doing this. The last thing I want to add is that this introduces a problem as well, which is that if I were to take this host and I move over here, I can't keep the address. It's not going to work. It's like saying I get a 519 phone number from a phone and I move to Vancouver, but I can't keep my 519, right? The number's got to change because it has geographical significance. Phone numbers have geographical significance just like IP addresses. So you can't keep it when you move somewhere. And that has some other consequences when you have mobility and roaming and so on, which I won't talk about right now. Okay? So the way the internet works, I'm going to now finally touch upon how we make it scale up. The way the internet works is what we'd have is that each of these bottom level things is called a subnet. Okay, and the subnet is sort of a bunch of addresses which share a prefix. Okay, then these subnets together form this big thing over here, and this is called a network. So let's, for example, call this the network 00. Then all the addresses are actually going to be prefixed by 00. So we're going to have this address actually 001100. This is 00, 001010, 0000, and so on. They're actually 6 bits long, for example. Okay, and it's all 00s in the front. Okay, so they're 6 bits long. But inside here, we are ignoring the leading 00s because they all have the 00 anyway, not giving answer. And we call this the network 00. And here we have the network, for example, 01. Okay? And we have network 10, network 11. And the way it works is like this. Whenever, let's say this router over here is going to have the special orange link to the next level up, this one over here. When you see a packet, any of these guys sees a packet which starts with 00, they know what to do. The destination is, in this case, 0000, 0001, 0. It knows what to do the next stop. But if the destination is anything else, which is called the default route, you're going to say give it to 01. Give it to 01 because 01 knows what to do. Right? What is 01 going to do? Whenever it gets something that is anything else, it just gives it to the next guy over here, this router in the center, okay? Which is called the core network. This is the core. In the core, what happens is it looks at the top 2 bits, and if it's 01, for example, it'll give it there. If it's 10, gives it here. 10 gives it there. And so it routes it over here, and then after that, we just do the opposite. It's just like writing a letter. Right? If the destination says, my country is Canada, you don't really care. Just ignore it and you just route it locally. But if the destination is Ireland, then we're going to give it to the head post office. And the head post office says, hey, Ireland, it goes over there. And then the Irish post office takes care of the rest. Okay? This works. That's why I said it can recurse and makes it scalable. So we can make this as deep as we wish. We have, so if you have 4 bits, we get 16. If you have 6 bits, we get 16, 32, 64, right? And so on. We keep scaling it up 2 bits at a time or 4 bits at a time, doesn't really matter. And we can make it as deep as we want. In the internet today, actually, it's a 3-level hierarchy. We don't have very deep hierarchy. We have the subnet, we have the network, and then we have the core, and that's it. Okay? Inside the core, essentially, everybody needs to know how to reach everybody else. And how that works is that it has very large routing tables. Okay, we actually haven't solved the problem of large routing tables in the internet today. Today's internet routers in the core have about 80,000 entries in the routing table, 80,000 entries over here, and it's growing slowly. It's going to be 80,000. Sometimes, some of them need 100,000 and so on. And that's what makes them very expensive. Okay, you can spend up to $1 million on these big routers, in part because these are very, very large routing tables. And that's in part because we only have a 3-level hierarchy. If you got to act together and had a 5-level hierarchy or 6-level hierarchy, everything would be cheaper. But then you run into other problems, in terms of ownership, who owns what and so on. Okay, but yeah.
So there's only one core.
There's only one core. Yeah, everything in the core knows exactly how to get. So they have tables like the first table you saw. It's random. Inside the core is random. So you need a table entry for every single network which way to go. Yeah.
And the core is all actually wired together.
Well, they're not directly wired to each other. This is a conceptual map of the core. Core is not fully connected like this. It's actually a graph, and I'll talk about that in a minute. Okay, any questions about this so far? Yeah.
So there are only around 100,000 those kind of subnets.
Yeah, that's right. Remember the ASs?
Yeah.
AS is basically a network, right? So there are about 100,000 of those. Yeah. So Waterloo is 12093. That's a network number, and then it corresponds to an address allocation of 12997. Yeah. Yes.
Last month, Waterloo ran out of IP addresses in residence because they just have too many devices connected.
Yeah.
What caused that? Why can't they just delegate more IP addresses for devices?
Okay, so basically, can you just hold that for a moment, because I'm going to come back to that. I just want to get the concept across, and then we'll dive straight into IP in just a moment. Okay. Any question? Because I want you to get this concept. Honestly, most people who are internet researchers don't understand this. Okay, the notion that IP addresses are geographically linked, and it's because of routing table and how the core works and so on, and how the subnet and network works. Funnily enough, most people don't actually understand. Internet researchers don't get it. So if you get it, it's actually pretty good. Yes, Ishmael.
So pretty much we can view the whole world as a bunch of these
Networks.
that are linked to the core.
That's correct. That's exactly right. Yeah. Yes.
The core seems sort of abstract. Could you define it?
I will. When I talk about it, we'll talk about how the core works and so on in like next class, and talk about routing principles. Yeah. But right now, I can assume it's fully connected. It's not. But we'll talk exactly how it works in a bit. Yeah. Okay. I just want to get the concepts across. The main concept here is that we have to have geographical addressing, and we have to have hierarchy. Otherwise, things are not going to work scalably. And we're making this trade-off, and we give up on portability because of that. Okay. Let me continue with. So I talked about this concept. So I'm just going to write down the concepts we talked about. So we have addresses. We have forwarding, which is how we send the packets on. We have the notion of routing, which is how the routing tables are made. We have the notion of geographical addressing, and then we have a hierarchy. I wanted to make sure these are the concepts that you guys should be familiar with. And then the notion of a network, number, and the subnet number, which is basically the different levels of the hierarchy: the subnet, the network, and then the rest. Okay. Okay. So how does this actually get put together? So I'm going to briefly talk about the hardware instantiation, just a couple of minutes, and then we'll get into a little bit more about how we deal with IP addresses. So. Okay, so how does this actually work? Well, at the bottom level, we have things that are called hubs. And the hubs have these little sockets, and then these are called ports. And when you have a desktop computer or a laptop, we attach a wire to a port like this. On the other hand, you can also have hubs which are wireless. And then you can have a laptop or something like this, and it connects wirelessly. But from our perspective, it has as many ports as there are wireless connections. They're not really ports per se. And then these hubs together will connect to some kind of thing called a router. And the router has ports as well. These are the ports over here. The thing about a hub is that it doesn't have any routing. It does exactly what broadcasts, right? If you send anything here, all the other ports get it. So we don't need to do any specific routing. Anything that's connected to the same hub, all the elements connected on the hub are connected to each other, okay, so automatically. And similarly, all the elements connected wirelessly to the same hub are connected to each other through that hub, okay? And these hubs typically correspond to subnets. So this whole thing over here will be one subnet. And there's another subnet. Though it's not an exact match. I'm going to leave we're going to come back to that. And these subnets are attached to certain ports. For example, you'll say, any sort of the subnet number is, I'm just going to give it names like A.1. So A dot star, for example, and this could be B dot star. And so we'll say the subnet number is A, the subnet number is B. So all the addresses inside that subnet will start with the same prefix A, which is the subnet number. It's like what we saw earlier. And the router is then connected to other routers, some other way. And what we have is a routing table over here, which basically says for a particular network number, which output port to use. This is called a port. And so ports actually have two directions. We need to be careful. We have stuff going in like that. So this part of it, which is where stuff is coming in, is called the input port. And this stuff over here is called the output port. So because it's going in and it's going out. And so of course we hook the output port of one router to the input of the other and so on. And well, that's basically how the network layer looks. We have hubs and ports and routers, and some of these links are local and some of these are very long. So if you have you saw in your assignment 1, for example, that there was a link from Toronto to a place in Germany, I forget the name right now, somewhere in Germany, right, on the way to Beijing, right? So you go Toronto, this player Eisen something. Does anybody remember the name? Something, yeah. And then Germany, and then Beijing, right? So these wires actually are wires going all the way from Toronto to Beijing. It's a very long wire, okay? And that's sort of the physical instantiation. And what we'll do in a few lectures from now, we'll look at exactly how to build these bits of hardware. But I'm not going to talk about that right. So there is some reason how it's put together. Okay. Any questions about this over here? Okay. Now I'm going to continue with the next thing that I really want to talk about, which is IP addresses. So IP addresses, so IP is the Internet Protocol. So first let me tell you a little bit about IP. So IP is often called so the Internet is often modeled as what's called the hourglass model. This is the hourglass model. If you know what an hourglass is, it's got sand on top, it's got this narrow point in the glass, and then sand drips through it at the bottom, right? Everybody's seen one. IP is the narrow part of this. And the reason is because above it we have TCP, we have UDP, and then above that we have lots and lots and lots of applications. And below IP, we have different kinds of links. We have wired links and wireless links and stuff like that. But everything goes through IP. Okay, you don't have a choice. Everything has to go through IP. So IP is this one thing that we all agree on. So IP goes on transcontinental wireless links, wired links. It goes on local wireless links. It goes on, whatever it is. As they say, the guy who invented IP is a guy called Vint Cerf, and he was very famous for this T-shirt he used to wear, which he used to call this. So that was a T-shirt he used to wear a lot. Okay. Okay, you might get it someday. Who knows? Okay. Okay. So the way that yes.
Oh, I just got a little bit confused because I remember TCP and UDP are two kinds of IPs, right? Or
No, TCP and UDP are transport layer protocols. This is at the network layer. Yeah. Okay. So one aspect of IP is forwarding packets. One aspect of IP is actually the routing protocols that come with IP. But the aspect I'm going to focus on right now is what I call IP addresses. And these addresses follow the hierarchical rule that we talked about. So an IP address, or IPv4 address to be more precise, is 32 bits long. And it's written like this, A.V.C.D. And you're familiar with this, where each A is, the A, B, C, D are all in the range, 0 to 255. Okay? So that's how we represent these 32 bits. And we have hierarchy in there, okay? So we have hierarchy because it's geographical. And so let me now talk a little bit about how that hierarchy is expressed. So let's take an address like let's take an IP address 129.97.24.2. Let's say we take this address over here, okay? So when a router gets this address, it kind of has to decide which part of it is the network number, which part of it is the host number, okay? Right? Because it's not going to make decisions based on the entire address. So in the routing table, it's going to have something like 129.97. Star, for example, okay? And then it's a destination, and then the next hop, right? So it could either have address like this, or it could have address like 129.97.24. Star, okay? So if we have a routing table of this form, okay, the first thing we do is we have this notion of using the longest match, okay? And the reason is because if you go back to the earlier picture, I should have left it on, I guess. Yeah, let me just go back to the hierarchical picture for a moment. So we had this one cloud like this, and inside the cloud we had sort of these subclouds. And then this one special guy is connected to, and these had these other clouds as well hanging off of them, okay? So let's say that this one over here is 129.97. Star. That's the network number, okay, corresponding to this network. And let's say this one over here corresponds to 129.97.24. Star. Okay, that would be that subnet over there. So in here, everything starts at 129.97. So they really need to have destination rules of this form, 129.97.24. Star. But everywhere else, they don't really need to have that information. All they need to know is that if it's over here, for example, it needs to know that 129.97, well, that means to go over here, right? We don't really care what comes after it. That makes the table quite short. It's just 129.97. Everything that's 129.97 goes over there, okay? So, so what we need to do is sort of have these rules that tell us where these break up. And the way we do it is by using what's called a net mask, okay? And the net mask basically says which part of it corresponds to the network number, okay, or the subnet number. So for example, over here, when we want to say 129.97. Star, what we really write down is 129.97.0.0, and then we say /16, which means only the first 16 bits are relevant, okay? And similarly, when this network got allocated the address, okay, it got allocated 129.97.0.0/16, okay, which means ignore everything else after that. Who allocated that to this? That's given by an organization called AARON, and I forget what AARON stands for right now. Assigned Registrar of Internet Names, or something like that. I can't remember what it is. But AARON is the one that allocates it. So Waterloo goes to AARON and says, the university, give us some addresses. They say, okay, you have 129.97/16, okay? And when it gets a /16, it says, okay, everything after that, first 2 bits is yours. Do whatever you want with it. And that's how we allocate it. And then what Waterloo does is it tells these routers in the core, I'm responsible for all addresses that start with 129.97/16. Okay, just send it to me. I'll take care of it. You don't need to know how. And that's the way we do that. So these routing tables all say, okay, this goes to Waterloo. Don't worry about how it gets routed inside Waterloo. And that's true for other places as well. They'll have other /somethings, right? Inside Waterloo, however, /16 is not enough. Here we need to have basically this one, which is we call a /24, which means the first 24 bits, okay, have significance. Okay, it's just a coincidence that it's 24 over there. Okay, but we could also have 129.97.12. And this would also be a /24, which means take the destination IP address on a packet match the first 24 bits, and if the first 24 bits correspond to 129-12, then send it to the next hop. Okay, that's the meaning of a /24. And the reason why we need this mask is because this is the way we express how many bits are significant in the routing table. Okay, and the rule, as I said, is we try to find the longest prefix that matches over here. Okay, so we find the longest prefix, we match it, we know what the next hop is going to be. Okay. All right, any questions about this over here? Yeah.
So my original question was, if there's only 4 levels of hierarchy,
Three levels.
3 levels.
Yeah.
Why would it take 30 hops to get to China? But learning this, would this mean that there's an upper bound of 32 hops because there's only 32 bits?
No, there isn't, because inside this thing is not. This is not a fully connected core. It's actually a graph, and I'll get to that question when we talk about routing inside the core. Okay, but yeah, yes.
Does that mean like a full IP address without the star on the end would be subnet mask 32?
That's correct. It would be corresponding to subnet mask 32. Yeah. Okay. So the point I want to get across is that these slash is only applicable to routers for the most part, and to people who get allocations. So if Aaron comes and gives you a /16, that means you actually have 2 to the power 32 minus 16 addresses, which is 2 to the power 16. If it gives you a /24, then you have 2 to the power 32 minus 24, which is 2 to the power 8 addresses. Okay, and so on. If it gives you, so that question on the top says, what are 2 consequences of all allocations being /31? That means that Aaron is giving everybody 2 to the power 32 minus 31 equals 2 to the power 1, okay, which is just 2. So it's going to give everybody chunks of 2, which means that your tables over here are going to be, /31s, okay, which means you're going to have lots and lots of addresses to deal with. Okay, so what happens then? Okay, that's the consequences that I want you to think about. Okay, so let me try and put that all together. So first, I want you to understand that IP address is 32 bits, not 4 bits, right? Second, just like we talked about earlier in the simple example, we do have this notion of hierarchy. We have this notion of a subnet and a network. And the important thing about hierarchy is that once you're outside your network, the rest of the world only cares about your network number. They don't really care about what your subnet number looks like. Okay? Nevertheless, we need to have a way in which we can refer to these addresses. Just a minute. Okay? We need a way to refer to these addresses which are sort of partial addresses outside. And the way we do that is using this thing called a net mask, which tells you how many bits are relevant. And this is done by an address allocation authority, which is Aaron, and it gives you a certain number of addresses. Okay, so it says your network number is this. And again, in the assignment, you found what the allocations were. When did you get them? By the way, Waterloo got its allocation on October 25th, 1987. So those of you who got 1999, that was our AS number, not the IP address, but I gave you a mark anyway. Okay. Yes, you had a question.
Yeah, so I was just wondering what network they're routing to is from, because you just said it's for the second one.
Okay, got it, sorry. So I should be more careful. Inside this over here, you can discuss it after class, okay? So inside this network, we're only going to have these kinds of entries. And then outside, we're going to have these kind of entries. So they're not in the same routing table. Yeah, I'm sorry about that. I should be clarifying. Yeah. So inside, we need subnet routing, right? They all have the same network number. It's no point. Outside, we only have the network layer. Network number, I'm sorry. Yeah. Any other questions? Yes?
You might have mentioned so the 3 levels of hierarchy are network, subnet, and host.
And the core. So core, network, and subnet. Core means basically you're going to use the network number to route it. Inside the network, you're going to use the subnet number to route it. Inside the subnet, you're going to use the entire IP address to route it. You're not going to use any part of it. You're going to use a /32. Yeah, Tommy?
I don't get why we use the slash notation, because can't you just figure out the number of addresses they have based on where the star is?
Oh, yeah, but as it happens, we can't write star at zeros and ones. There's no magic symbol star. If there were, it'd be okay. Star is, it's not a 0 or a 1. Yeah, if we had ternary logic, we could use it, but we can't, so we use a mask instead. Yeah. Yes?
So when I was trying to find out my address at home, I saw the subnet mask was 255.255.2.
Yeah, yeah. Yeah.
The last one was
Yeah, so 255.255, it's another way of writing it. .255.0 means basically 1111, whatever, 8 ones. So this is 24 bits basically, okay? They're all ones, so this would be a /24. So this is another way of representing it. You're right, I should have mentioned that. So we can represent the mask in two ways, either a /24 or 255.255.255.0. This is the way it's actually represented because it's zeros and ones. And this is the way we represent it because, again, slash is not a 0 or a 1 either, right? So we represent it in this form. So that's the actual representation. Just a consecutive series of ones that represents which part of this entry that we need to look at, and the rest we can forget about. Yes?
So the higher the number after the slash,
Right. Fewer the bits.
less mask.
That's correct. No, the higher the number, it is the smaller the block of addresses refers to. The smaller the block of addresses. So if you have a mask of, let's say, 16 bits, then the block of addresses is 2 to the 16. If you have mask of 24 bits, right, the /24, you have only 2 to the 8 addresses you're referring to all at once.
What you said a little while ago with that is throwing me off. Then why is it a problem to have a /31?
Because you're getting blocks of 2 addresses at a time. You're getting blocks of 2 to refer to your network. So your network is going to have, so if Waterloo has 10,000 computers, you need to have 5,000 blocks of 2. And all 5,000 blocks of 2 have to be in these guys' tables saying, yeah, Waterloo is responsible for all those 5,000 blocks of 2. Right? So the table is going to be, beg your pardon? If you had a /31 in this question over here, if the allocations were all /31, we're going to have many, many, many network numbers corresponding to Waterloo, not just one.
So the lack of hierarchy makes it more complicated.
It's not that it's a lack. Yeah, you're not aggregating up very much. You're just going to have everything small aggregation. Okay. Any other questions over here? Yeah.
So the core has its routing tables mostly filled up with subnet mask 16. The network's mostly filled up with subnet
24 mostly.
Subnets.
Yeah, that's correct. Yeah. Yes.
So if you run like a big company where you don't want all of your computers to be like directly routable on the internet, you
Right.
can just get one address?
Yes, you can.
Subnet everything?
Yes, you can.
So then why are we running out? It's on the whole of it.
Well, there are many reasons why, but yeah, it's also historically it was allocated differently. Yeah. Okay, I'm going to kind of pause on this. If there are more questions, please post it on Piazza because I can answer more about this. I want to now briefly talk about what the IP looks like, so I can get to the second question. And I just want to mention 2 fields in the IP, and then that will allow you to actually answer the second question. So let's see. So the IP packet has got a header, and it's got a data. Okay, and what I'm going to talk about now is just what's in the header. The data is whatever it is. So the header has a bunch of different fields. So one field is the version number. Okay. Excuse me, can you just, yeah. So the version number tells you what version you're running. Is it 4 or 6 and so on? And it's a good idea to have version number in case you change the version later on. There are a bunch of other things which I'll talk about later, but I'm going to talk about 2 things right now. One is the source address, and one is the destination address. And these are 32-bit fields. And the source address says, where is it coming from? What's the IP address of the source? And the destination address is what's the IP address of the destination. Okay? And these are sort of the most important fields because they tell the network what to do. So in the header, if you look at it, you'll find this source. So destination address is used to route the packet. So what happens is that the packet with a particular destination address goes to the first hub. The hub looks at it and says, is this address matching one of the computers connected directly to me? If not, it says, okay, I'm going to give it to the router. The router looks at it and matches it with its routing table, okay, and finds from its routing table whether it matches one of these, whether it matches any of the next hops, okay. If it does, great. Otherwise, it goes into what's called a default, which says, I don't know what to do with it, right? It's like a local postman says, I don't know what this Irish address is. I'm just going to give it to the main post office, let them deal with it, right? So that's what happens as well. The router is going to say, okay, I don't know what this means. I'm just going to give it to the next level up. That is going to try and match it. Okay? If it can't find it, it gives it the core. The core is guaranteed to have a match for every single destination address prefix, right? So because it has these 80,000 different entries. So it looks at it and says, okay, I know what the next hop is. Off it goes to the next hop. And this process, the next hop happens, okay, because it's not fully connected, it can take multiple next hops. And finally, it gets to the network number that it belongs to. And that says, okay, now I can give it to my subnet. And so it happens, right? So we need the destination address to get there. Do we need a source address? The answer is actually what? Do we need it or not? Yes? No?
Well, if you're sending it back.
If you're sending it back, if you need a response, right. But if you don't want a response, then you don't need it. Exactly. It's like sending a letter in the mail. You don't need to put your your home address. You can just mail it, right? It'll get to the destination. So this is what's used to spoof, okay, a source. Spoofing the source means setting the source address not to yourself but to some other person, right? Okay, it's like putting a false return address on your envelope, right? When you do this, the reply is going to go to somebody else. Why would you want to do this? Okay. You want to hack into somebody's computer and you want to send them millions and millions of packets just to, choke them up and cause their website to go down. You don't want to put your own source address there, right? You'll spoof the source address because it's not needed, right? IP has no intrinsic way to prevent spoofing. You can put any arbitrary source address you want and put it in, and unless you do something special, right? Unless you do something special, it's going to be forwarded to the destination, and that's a problem, okay? So the second question says, think of one way in which you could prevent this from happening. How would you invent a technique that would prevent source addresses from being spoofed? And remember, you have to think about, I'll give you a hint, what you have to remember is that IP addresses have what? Geographical significance. Okay, so if I put a random IP address, then, okay, maybe I have a, now I'm almost giving the answer away, but think about what would happen if you put a random IP address as your source address, given that it has geographical significance. So that's the part I wanted to get to. So what I'm going to talk about on Thursday is I'll talk more about the other fields in the IP header, and that will give us a good kind of insight into how we do routing and stuff like that.